Hi, I'm Darin from Imply, and I'm here to talk to you about how is Druid so fast. Apache Druid is known for being able to take really big data sets, petabytes, tens of petabytes, and be able to do queries in seconds or even sub-seconds. How is that even possible? Well, let's talk about how. It's a combination of segmentation and scatter-gather queries. So let's start with the segments. Now, data is going to come into Druid from one of two sources. It could be coming in from some sort of file. So this is what we call a batch ingestion. It could be a file, a database, but something else that's batch. Or it could be coming from some sort of stream. So this could be Kinesis or Apache Kafka or something else with a Kafka API, Confluent, Red Panda, Azure Data Hub, whatever. And then these are both going to send information into my database. Now, if the data is coming from files, it goes directly into segments. If the data is coming from streams, it goes into memory, so it's immediately queryable. I don't have to wait. The sub-second that the event arrives, I'm able to run queries on it. But after a period of time, it will be turned into a segment as well. So what's a segment? It's a file. It's what I'm actually keeping the data in. So we usually want it to be somewhere between 300, 500, 700 megabytes, usually a couple of million of rows of information. That's where I get my best performance. And it's going to store that file as columns. So columnarization has a couple of advantages. So first of all, it's going to save me some space, especially for columns that are low cardinality. And cardinality is just a fancy word for how many unique values there are. So let's say this column is country name. There's less than 200 countries in the world. So I'm going to have less than 200 values there. So even if I have millions of lines, I'm never going to have more than a couple of hundred rows in that column. So I only have to do each country once, and then I can use indexes to map it to the others. But this column might be high cardinality, maybe session ID. So that's going to be everyone unique. So with 100,000 rows, I'll have 100,000 session IDs. Okay, that won't save me space. But columnization still saves me on queries, because if my query is only querying columns 1, 2, and 3, bam, 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 I don't even have to look at column 4. So it saves me some time. Now, this is something almost every analytics database does. It's not unique to Druid. Druid, however, takes things a few steps further. So first of all, the data in here is indexed. So these country names will be bitmapped into a dictionary encoding, and then they'll be stored as numbers. And there'll be a dictionary that lets you translate those numbers back out into the text, but that makes things even faster, more compressed, less space, quicker queries. If this is a numeric field, then I don't bitmap it, but I still index it, and I compress it into a set of numbers that might be repeating, which allows me to do some really good storage and take up less space. So you don't have to manage indexes in Druid. It just happens. Indeed, it's only the index that actually is getting stored. So I've got that data available, and from it I can recreate the original data, but it takes up less space and it can be queried more quickly. So I've got indexes, I got index and bitmapping, and then the whole thing is going to be compacted and committed. So what does committed mean? Well, when I write out my segment, in Druid, I'm going to have a Druid cluster, and my Druid cluster is going to have one or more data nodes. So each data node is going to have some storage, that's what this is supposed to be, and some processor and memory, which is what that's supposed to be. So there's a node, and there's another node, and there's another node. And, a real cluster, well, the smallest possible cluster is one laptop, and the biggest possible cluster really isn't a limit. There's some people out there who have tens of thousands. So this is where my data is actually going to end up landing. And when I'm ready to commit this segment, the segment will get written in. It'll get written to at least two different places. So let's say this is node A, or segment A. So I'll put it writing on this node and writing on this node. And I'm also going to put a copy into what's called deep storage. So deep storage is a durable and reliable storage environment. If you're on the cloud, it's object store. So Amazon S3, Azure Blob, Google Cloud Storage. I have another copy there. Now, I know I'm supposed to be talking about speed, but let's take a minute to talk about reliability, because it's one of the other cool things about Druid. I'm not going to lose data. I'm not going to go down. My next segment B might go here and have a copy on deep storage. And my next segment, C, might go here and have a copy on deep storage, and so on. So let's pretend that this node failed, that this server goes down. Well, Druid's smart enough to say, I only have one copy of B and one copy of C now, so I'll write an extra B over here, an extra C over here. Let's say I lost 2 nodes. Well, now I don't have any copies of B, but I can copy it off the deep storage onto another node. So when I lose nodes, it's not a failover, it's seeing the damage and working around it. And the deep storage is super durable. I mean, Amazon S3 is 11 nines, 99.9999999% durable. It's really hard to lose data because it's not really one copy. It's many copies in different data centers across an Amazon region. So I put those things together and I have really highly durable storage. I'm only going to go down if I lose like all the nodes, which is possible, but rare. And even if that happens, I don't lose the data. So we have an environment that I don't lose data and I don't have downtime. And for that matter, if I need to do upgrades, that's all rolling upgrades. I never have to take it down. So a highly reliable and dependable environment. But let's get back to speed. So I'm going to go do a query on here. And that is going to be processed by a query node. So when I actually do a query, I'm going to write a query. I'm going to use SQL probably. And it's standard SQL. So I'm going to do a select statement. I'll select column 1, column 2, column 3. And I'll select it from whatever my table name is. And I don't want the whole history of this. I only care about the last, let's say, 10 hours. So I'll do a where time is greater than, and then I'll just do I'm just going to pseudocode this, but a current time minus 10 hours. And the actual code will be a little longer than that. So now when I execute this query, it's going to go to the query node. And the query node is going to say, I only care about the last 10 hours. So I might have millions of segments here, but I only care about, let's see. Yeah, let's say this was, we said this was going to be about 100,000 events per second, about 1K per event. So what is that going to be? That's going to be about 3,600 segments. In addition to, of course, the one kind of virtual segment, that's the current 10 seconds, which is data still coming in, which is there in memory and still queryable. So I'm going to have the query node go, well, I want to talk to at least one A, and I want to talk to at least one B, and I want to talk to at least one C, and I want to talk, and so on, and go across this entire set of data, scattering the query out to be able to talk to those segments. And then they all process in parallel, and of course, return their data back up to the query node, which gives us back our answer. So I'm not really doing what would be about a 1.8 terabyte query. I'm really doing 3,600 500 megabyte queries. And if I'm querying, say, a full terabyte, I'm not really doing a terabyte query. I'm really doing 2,500,000 megabyte queries. That parallelism, combined with the intelligent segments that makes each query super fast, lets us do entire queries in seconds or subseconds every time. This is what makes Druid so fast. But there's some tricks we can do to make it even faster. So one of those tricks is called a roll-up. So let's say when I'm doing these queries, I don't really need all the data. Let's say I only care about what happened in each second. Well, I could roll it up by second. So right now I've got a row per event. So if 100,000 per second, then, in 10 seconds, I got 1,000,000 rows. If I do a roll up by second, now I only have 10 rows. Now I won't get as much granularity, but depending on what I want to query, that might be good enough. So I can use roll-ups to radically reduce my data size and therefore radically increase my speed. Or I can do approximations. So the most common approximations are something called a theta sketch and another one called a hyperlog log. Now these are really cool mathematic transformations that I'm not going to go into the great details, but I'm going to tell you what they do is they let me get approximate readings really, really fast. So one common use of a theta sketch is if I need to do a count distinct. So let's say this data is actually clickstream data. And let's say I've got a couple of years of clickstream data, maybe a few billion rows. And this column is what websites people visited. And I want to know how many different websites did the people I'm measuring visit in the last year. Well, in SQL, you do that with select count distinct. So if I do a select count distinct across this large section, it's going to take a long time because I have to look at each of millions of rows or billions of rows. But if I set up my table with a theta sketch, then in less than a second, I can come back with an approximation. Now, it won't be the exact number, but it'll be within 2%. And actually, the larger the data set is, the more accurate it becomes because of how the mathematics operate. So if the correct number of different websites might be, say, 1,082. And the answer I'll get back with this query using a select count distinct with a theta sketch might be 1,067, might be 1,102, but it'll be within 1 or 2%. It'll always be within 998,000 and 1,002,000. And for almost any time I'm doing this kind of work, that's close enough. Because I don't really need to know the exact number of websites. I need to know, is it about 1 million or about 500,000 or about 5 million? And that'll let me do it. So, intelligent segmentation, scatter gather queries, scattering it out across all these data nodes and gathering it back together, and optionally roll-ups and optionally approximations give me a whole bunch of tools to be able to take really big data sets with live data coming in and get real-time analytics in context really fast. Now, if you'd like to know more about this, please Imply.io and then take a look at the Druid Architecture and Concepts white paper or some of the engineering blogs. A lot of good information there. But whatever you do, go do some cool things with analytics. Thanks.